Hi, this is an introduction to neutral geometry, or what some folks call absolute geometry. So if you look this up in Wikipedia, for example, and Wikipedia is pretty good on their geometry content. I'll stand by it at least, in early 2021. And they'll call it absolute geometry. And all it means is that we're going to prove everything that we can in a typical Euclidean geometry development without assuming anything about parallelism. Okay, so what I'm going to try to do is explain why this is important. There's two reasons. First of all, there are three different, very different types of geometries that can arise when we allow different parallel conditions. Okay, so when there's no curvature in the system, we end up with this plane geometry, Euclidean geometry that we're used to, where triangles have angle sums of 180 degrees, lines don't have any curvature, um, the area of a circle is equal to pi, and there's exactly one line here that's parallel to, um, well, this is Playfair's postulate, right? Through given a line L and a point P naught on it, there exists exactly one line through that point that's parallel. Okay, well, so positive curvature, that's a elliptic geometry or spherical geometry, right? And here notice that we have fat triangles, right? They have angle measures that sum up to more than 180 degrees. And the area of circles is greater than pi, and we don't have any parallel lines at all. And notice that we have positive curvature on our lines, okay? Which means that they curve into each other. All lines are finite, right? You can't go off to infinity at the sphere. They all cross. So then our third possibility is hyperbolic geometry, okay, where now we have thin triangles, right, where the angle sum is less than 180 degrees, and we have these lines that curve. This is called negative curvature. And here we have, and I don't particularly like this parallel drawing. What we have is we have infinitely many lines parallel to any given uh, line through a point. There are infinitely many lines that are parallel to it. So let's take a look at what we mean by that. So I set up a or I included an animation of the hyperbolic disk, and this is a little bit seizure inducing if you're not expecting it, which is why I put it in this little drop down box. Um, and what is it describing? So this is the famous Poincare disk model of hyperbolic geometry. Now the distances, I have to explain, are very different at the edges of the circle. And tiny little distances near the edge of the circle are very, very big. In other words, um, well, let me explain. So we have these rectangles opening up. So you can see, right, that you have these sort of diamond shapes opening up everywhere, right? And they're rectangles. Now, I know they don't look like rectangles. I'm not trying to pretend they look like rectangles, but they're definitely quadrilaterals, let's say. And and these lines aren't straight, and you can see that that given one of the sides of this quadrilateral, there are lots of points in the geometry that don't intersect it, that never touch it. Okay, and so this is what we mean by negative curvature. And that means when we have negative curvature that we can have infinitely many parallel lines. Okay, so what does that mean for us as we start to develop what we might call regular geometry? You're like, come on, I mean, why do I care about all these crazy geometries? I just want to know about Euclidean geometry, and that's fine. But the difficulty with Euclidean geometry is we didn't know if a parallel condition was necessary, right? That was Euclid's fifth postulate. Um, and again, most people use Playfair's postulate in place of Euclid's fifth because it explains it better. And Playfair says that, right? Given a line L and a point P that's not on it, there exists at least one line parallel. Why at least? Well, we can prove that parallel lines exist, so we know that there's a line there. The problem was what we couldn't prove is we couldn't prove that there was exactly one line. So Euclid's fifth postulate was correct, that there always has to be a parallel line. We can prove that in neutral geometry. What was the nuance that they couldn't quite figure out was what kept there from being infinitely many, and that's not really what they were trying to discover, or what Euclid was confused about, or maybe he was, but that's the nuance that confused people for a couple thousand years. So it's a really interesting quest, and so this neutral geometry section is going to go through this quest where people try to figure out what in the heck was going on. I mean, really, what in the heck was going on with this parallel condition? So what's the best way to do it? Well, why don't we prove everything it's possible to prove using a standard Euclidean setup, but without assuming any parallel property at all? And that's what we're going to do to start this section on Euclidean geometry. We're going to start in neutral geometry, and we're going to get as far as we can in neutral geometry before tackling, well, at some point we do have to choose a parallel postulate, so that we can rule out some of these other models of geometry. But we're going to go as far as we can before we have to do that. When I refer to the standard Euclidean setup, what do I mean? Well, there are lots of different axiomatic systems that we can use to create a Euclidean geometry. And some of them are really good mathematically, and some of them are really good teaching wise. And so what we're going to use is the SMSG axioms. And why? Well, the difficulty if I use some of the more mathematical ones is that, yeah, they're great for college geometry courses, but you spend a lot of time proving things like about the properties of real numbers, which we'd really like to just assume. This is what Birkhoff's axioms do, is they give us the properties of the real numbers. But if we start with something like Hilbert, we spend a good bit of our time proving things basically that come down to the continuity and completeness of the real line. Well, what the SMSG axioms do is they assume that all lines in this Euclidean geometry are exactly like the real line, and they're continuous and complete. And if you want to look at some of these properties that we just get to assume, you can check out these two videos. So what we do with our school mathematics study group, is we get to assume that all of our basic set theory is true, right? We have operations like intersections and unions. We have inclusion, set inclusion. So we have elements like points being contained in sets like lines, or we have elements like lines being contained in sets like planes. We have the intersection of two sets. We can use logic. So this means that our formal proofs work, right? That we don't have to prove that a proof by induction is legitimate. We can just do a proof by induction. We don't have to say that it's possible to prove by contradiction or contrapositive. We just use those logical structures. And then the final thing is what I was talking about a second ago, is the algebraic properties of real numbers, right? Things like that I can do some substitution. Things like I can do cancellation. I can add one thing to both sides of the equal sign, right? So these algebraic properties of real numbers, if I'm working on equations and the field that I'm working on is the real number line, then all of that algebra that I can do in high school is legitimate. And things like when I am working with an inequality and I multiply or divide by a negative number, it flips the inequality. Those types of things are what we mean by the algebraic properties of real numbers. And when we end up being able to create equations, we are allowed to use these properties to solve them. So we're going to use these algebraic properties of real numbers because they're this huge ski jump and they send us flying past a lot of tedious proofs, like the fact that the square root of 2 actually exists and is a specific distance away from other points on the real line, right? We get to avoid all of those tedious proofs and do actual geometry proofs right away. And so the SMSG gives us immediately within the axioms, gives us distances and angle measures that are real numbers, right? And so we get these algebraic properties of real numbers right away. Also, because of the ruler postulate, we get continuity and completeness of every line. In other words, every line in Euclidean geometry has the same properties as the real number line, right? I can use a unit interval and create a grid of intervals, just like the coordinate plane. Distances work just fine on the real line. We get all of that. Okay, so let's take a look at the axioms just to see all of the power that we're getting here, right? So line uniqueness, and we're used to this one from finite geometry. Given any two different points, there is exactly one line which contains both of them. So that's an incidence axiom. The distance postulate. Now this is important. To every pair of points, there corresponds a unique positive number. And by the way, when we're talking about the distance between A and B, we just write AB. If I want to call it a ray or a line or a segment, I put I put a hat on it, right? I put some symbol above the A and the B. But if I just list A and B together, that is referring to the distance. Now here's the ruler postulate, which makes every line act like the real number line, right? So the points of a line can be placed in correspondence with the real numbers in such a way that we have these three properties. So every point on the line corresponds to exactly one real number, which makes sense. You're either 7.1 units away from another point or you're not. To every real number, there corresponds exactly 1 point of the line. Right, so wait, I guess I should have said it the other way, right? If A and B are 2 points, then B, whatever distance that is, 7.1, right? That's how far B is away. And there's not some other point in the same direction that's also 7.1 units away. And then the distance between 2 points is the absolute value of the difference of their corresponding real numbers, right? They're just saying that we can coordinatize the real, any line actually. And once I know where some baseline point is, call it the origin. And then I can use these real numbers from sections 1 and 2. And I know that if A is 5 units away from the origin and if B is 7 units away from the origin, then the distance between A and B is 7 minus 5, or the absolute value of 5 minus 7, either way you'd like to think of it. So that's really powerful. Now the ruler placement postulate, okay, so this says that I can take any line in the geometry, right? Just pick any 2 points in the geometry, put the line on them that goes there, and then we're saying that the coordinate system can be chosen so that, right, here's my origin, right, and the coordinate of Q is positive. That's my 1, right? So I have this unit interval defined. I just pick any 2 points in the geometry, draw the line that's on them, and then I have the real number line. And so this is kind of cool. It means that I can set my ruler down anywhere I want, and then I can re-coordinatize based on some known point Q. So, I mean, just look at this. This gives us so much power. And by the way, these are not particularly easy to prove. They're not hard, not extremely difficult, but it would take a while to prove all of these things. And we are going to use these really robust axioms to kind of push us past some of those tedious proofs. Here you go. Here's another incidence axiom. Every plane contains at least 3 non-collinear points, right? So I have that same kind of setup that I have at least 3 points, and not all points are on the same line, very much like the 4-point and 5-point geometry. And then space contains at least 4 non-coplanar points. Okay, so now we have the idea of a plane coming in. Okay, so plane uniqueness, there's at least one plane containing any 3 points, exactly one plane containing any 3 non-collinear points. So yes, we're getting a whole bunch of stuff in here with these axioms. Let's just run through the last of these in a little bit, just to give you an idea. It's really important to know what axioms you have at your disposal to help prove things. And plane uniqueness and isn't particularly important. It's kind of a useful idea, but we don't use it in proofs. Plane intersections, if two planes intersect, their intersection is in a line. Here, this one is huge, okay? So we have these ideas of Pasch's axiom and the crossbar theorem, and Euclid used the crossbar theorem a lot. But we're using this idea of the plane separation postulate to get those ideas across. So given a line and a plane containing it, the points of a plane that do not lie on the line form two sets. What? Okay, so you're saying we have a line. And on one side of the line, we have the set of points A, and on the other side of the line, we have the set of points B. Okay? Each of the sets is convex. What does convex mean? Convex means that if I draw 2 points that are in the set, and then I draw the segment between those 2 points, then the entire segment has to lie in that convex set. So they said if P is in one set, right? So I have P over here. Sorry, that doesn't look much like a P. So I have the point P over here and the point Q over here, right? The only way to join them is to cut across the line. And this is really valuable. And again, we'll look at this a little bit later when we look at Pasch's axiom and the crossbar theorem. The key thing really, it's surprising, but the key thing is this intersection point. In other words, there is a point on the line. The line is continuous and complete, and therefore, where this segment ought to go through it and intersect, there actually is a point of intersection there. That's an important piece. Space separation postulate. So this works the same with in 3D as it does in 2D. Here are some important axioms. The angle measurement postulate. So this is cool. So this is analogous to the ruler postulate, but for angles. So this might be called the protractor postulate, right? So to every angle, there corresponds a real number between 0 and 180 degrees. It's important to note that we don't have a definition of, say, 270-degree angle. That'll have to be something that we define later, these reflex angles that have more than 180 degrees. We have not defined it yet. We don't have an axiom that defines it. And so it doesn't even make sense to talk about reflex angles. So angle construction postulate is very much like our ruler construction postulate. So we're going to let A and B be a ray on the edge of the half plane H. And so what they're basically saying is that we have the x-axis and we have a ray that's pointing along it. And then it's just saying that there's some angle measure, right, that will determine where the second ray of this angle happens to be. And oops, in there I should have the measured angle symbol. Sorry, I'll fix that. And on this one too. Okay, so the angle addition postulate. Now this one's a little different than what we've seen before, but it does make sense that if D is a point in the interior of the measured angle BAC, wait, no, I don't, that shouldn't be measured angle, it's just in the interior of angle BAC, then the angle sum of these two angles, and I'll switch these to measured angles instead of M, angle. But, right, so here's what we have. We have this, and D's in here, right? That point there that I'm having trouble drawing is D. We're saying that if a ray goes through here, now I have two angles, but their angle sum is equal to the measure of the original angle. Then the supplementary postulate, axiom set brings up this term linear pair. So we have to define that. It's what you'd think. It's an angle, right? It's a pair of rays that are not the same ray, but together they form a line, right? So we have this linear pair. And if two angles form a linear pair, then they're supplementary. So I don't love this axiom. It sort of gives us some definitional problems, but hey, linear pair, okay, we'll go with it. Side angle side postulate. Now this one's important. This is the last one. By the way, 16, axiom 16 is the parallel postulate. So this is the last one we get before the parallel postulate. And it's side angle side. And this is really cool. It's a congruence axiom. And it basically says that if the side, if two sides in the included angle of one triangle are congruent to two sides in the included angle of another triangle, the two triangles are congruent. So this is great. Getting congruence from just the basic axiom, this is one of the hardest things to manage. But we get it for free using the SMSG axioms. And we'll prove the other congruence postulates or congruence conditions using this one.